Distinguished guests and colleagues, good afternoon. Today, we are honored to welcome an internationally renowned expert in ultrafast science and biophysics, Professor Dongping Zhong, to deliver a cutting-edge academic talk on ultrafast dynamics of complex systems in biology and materials. Professor Zhong currently serves as a chair professor in the School of Chemistry and Chemical Engineering, and he is a leader of the Center for Ultrafast Science and Technologies at Shanghai Jiaotong University. His academic career exemplifies the interdisciplinary research with groundbreaking contributions to femtochemistry, biophysics, and protein dynamics, and have profoundly reshaped our understanding of light-driven processes in living systems. Professor Zhong is a student of Nobel laureate the Weil, who is a pioneer in femtosecond chemistry. And Professor Zhong's research has consistently focused on the dynamics mechanism of key biomolecules, including photoenzymes and photoreceptors. Professor Zhong, actually, he has won a lot of awards, such as Fellow of the American Association for the Advancement of Science and the American Physical Society. He has served as an editorial board member for the journals such as Chemical Physics and the journal PChem. Without further ado, let's welcome Professor Zhong to deliver his talk.
Okay, thank you. 前面灯可以关掉吗？可以吗？前面不可以哈。OK， 拿一个快灯吗 ？Yeah. Oh, okay. Yeah, is this one? Is possible? This no? Yeah. Yeah, that's better. That's better. Yeah. Thank you, Professor Chen, very much, and also thank IAS and the Department of Chemistry for the invitation for this wonderful trip to here. I guess I came here several times before. Maybe I guess at least 2 times I came here before. It's a really great place to visit again. Let's think about this biology. Okay, since I'm doing the biophysical chemistry, in the past, protein, back to basic molecular proteins in biology. In past 10 years, we already had a big advance in protein structure, science. For example, the cryo-EM really a breakthrough for the membrane protein, for past 10 years. I still remember I was subabatic in Caltech in 2013, 2014. That was a really breakthrough at the cryo-EM in the December 2013. And then by famous Chinese scientists, I'm sure you know, to improve to the atomic scale for cryo-EM. So very soon, this field gave the Nobel Prize. You can see so many protein structures solved, especially membrane protein or bigger complex. And last year, we have another theoretical work for protein design and prediction by this Sunil Weilong, famous scientist or passionate scientist. Okay, so today, very routine. In every group, I'm sure you can use AlphaFold 3. You can really to predict or roughly estimate or calculate the protein structure. For a while, science and nature also push also very hard. Of course, in the whole field, the people push very hard. People truly believe to fully understand biology and to fully understand the drug design, we need to know protein dynamics. Especially today, with AlphaFold 3, people more and more realize only AlphaFold 3 is not good enough to design the drug, these days, by talking many experts in the field. So Nature and Science and also push hard recently and published a special issue about the protein dynamics. So in a sense, This is the post-structure age, and we welcome to the age of the protein dynamics, in the past probably 10 years, 20 years. If you look at the protein structure, when I was arrived in the US, I remember in later 1980s, that's only a few thousand X-ray structure in the PDB bank. And clearly you can see the structure grow exponential rise. Today we have close to 200,000, the protein structure solved by this really physical method like X-ray and micro-EM, etc. But if we use the AlphaFold 3, we can get a millions protein structure right now. And also accuracy is pretty good. Right now people believe by AlphaFold 3, the accuracy can reach to 50%, even sometimes to 70%. So it's not bad at all. So we really can reach, the structure, level, and then many people can do it these days. So back to this fundamental structure is okay. Function, many people doing for ages, and the dynamics is difficult. We are basically. Right now can do fundamental chemistry. Really, we can start small molecules, vibration, rotation, electronically, pretty very well these days for dynamics. And then biology is complicated because we can, covering from the ultrafast and to ultra-slow, and then since there's a bigger molecules, so motion is everywhere. In our lab, right now, we really can do dynamics from femtosecond, let's say 10th femtosecond, down to probably close to millisecond. So we can cover like a 12 order of magnitude of the dynamics and to really understand how protein function, hopefully help for drug design or for other things. Yeah. So in the past, in my group, basically we focus 4 or 5 directions. I list this 4 heavily studied. So one is in past 20 years in Ohio State, we spent lots of time try to understand the protein-water interaction the dynamics. So how water interact with protein, why protein is flexible but is keep a certain structure. And then we spend lots of time study photoreceptor, which I show you today some cases. And we spend lots of time to study enzyme dynamics here, especially photoenzyme and also artificial photoenzyme. These days very active, and I'm sure you know this. Artificial photoenzyme, by many people doing this. And we also in aspect of the physical chemistry, we study non-equilibrium dynamics, especially electron transfer, proton transfer, in terms of a little bit of theory model, and then quantum control, etc. So probably I will just show 3 maybe cases for this first 1 or 2, 3. Probably we don't have time to talk about it. Yesterday I was in the City University, talk a little bit of this one yesterday. So water. Water actually is a very interesting system. I'm sure even today it's still a fun system. I'm sure it's very hard to understand the water. So let's talk about this water and the protein. And here I show you we did the first experiment, apomyoglobin. And why we choose this actually is horrible. It was horrible. And this protein is very tough, And why we choose this as the physical chemistry at that time, many people started apomyoglobin, folding, molten globule state, all these details. Peter Walter in the script spent a lifetime to start apomyoglobin, myoglobin folding. So we choose this 3 system, and what we do, we need to put an optical label. Today, we know we can put the artificial amino acid or label, do all kinds of things. That time, 20 years ago, it's very tough. Peter Schultz just started to do the artificial or just invent artificial amino acid. So what we do is we put the tryptophan and as the tryptophan intrinsic amino acid as the optical probe. We put the once a time and then 1 by 1, so we can design, let's say, 35 mutant to map this outside this surface. What do we do? By laser excitation, UV light, we can look at the tryptophan fluorescence, the Stokes shift with time. And then we can extract the dynamics of the in 10 angstrom, because we consider dipole-dipole interaction. So it's in 10 angstrom, the environmental relaxation. And in this way, if we can design wisely and we can map out the more or less global water motion, that's the original idea. So, but I give you a little bit background. The water actually is a pretty interesting, the hydration water is a pretty interesting topic for many, many years. In 1960 or 70, biophysicists believe the hydration is the iceberg. It's a shear because the protein has structure. So it has to be, water has to be well-ordered structure to preserve the protein structure. But with the computation in 1980, at the end of the 1980, early 1990, and people find out by simulation, it's not like today, even that time it's not that trivial or easy, to simulate this water motion dynamics around the protein. People find out water is extremely mobile. At that time, in the physical chemistry field, people already know the free water moves within 1 picosecond at that time. So people say, oh, original people believe this is a shell-ordered water, but by MD simulation, people find out this is very mobile. It's a little bit slowed down, but by a factor maybe 1 or 2, and not too much. And then you will ask, say, how this protein can preserve the good structure only by protein free energy or also by the water? So that's the key question at that time. And then the MD pioneered by Mark Levitt at the early 1980s, Mark Levitt later on received the Nobel Prize. And also by a bunch of the very well-known cell tissue MD simulation. So we started this when I was a postdoc. At that time, the 3 giant fermental giants, Fleming, Robin Hochschild, Harman Zwell, we started to do this. Fleming and Robin Hochschild used dial labeling, but it's not site-specific. It's not site-specific. So basically, if you have a hole here, I maybe use hydrophobic interaction, I could put 1 dye here. And then we go to use Stokes shift or use echo, photon echo, we can measure the water motion around this region. Okay, I mean here, that time I started postdoc, I think, oh, this is tryptophan. We understand the photophysics, LA, LB, stuff. Then we say this also can be optical probe. So that way, use molecular biology technique, we can really put one at a time, 1 by 1, 1 by 1. Of course, you need to do lots of the molecular biology work, but we can do it. Theoretically, we can do it. So we did. So we did the apomyoglobin, and then we designed the 35 mutants, which is a huge work. And then each protein we need to purify 2 weeks at least, So you can think of the huge work. But anyway, among the 35 mutant, only like 16 mutant work. Many mutant doesn't work because either it's misfolding or it is the yield extremely low, or some mutant even not produce the protein at all. So anyway, we get a 16 mutant. And then we took this time-resolved spectrum, fluorescence spectrum. This is the experiment data. Of course, we put the 1 by 1, 1 by 1, then we just plot it this way. So by Stokes shift, we just look at the peak shift with time. And then by doing this, we can get a correlation function, right, but normalized. So if we are doing physical chemistry, we load the correlation function, we can do many things. So that means this correlation function basically is reflect the environment relaxation dynamics. And interesting enough, from the disorder data, you can see the blue light mostly is faster than red light. Blue light is faster than red light. And the blue light is pH equal 4, is a molten globule state. So right now you understand that if a protein fold the molten globule state is we call the transition state of the protein folding or intermediate state. So the hydrophobic core already formed, but the whole protein not formed. So in this way, you can see the water still not slow yet, not reach that slow yet, but it's faster than Y type. So that means the Y type, it is the water has more ordered. But in the modern global state, since not formed nearly Y type modern global native states, so modern global state, the water still not formed well ordered. So it's faster. Of course, you will ask, say, oh, I have one, this one, the modern global state water, it is slower than the native state. And then if we look at the structure very carefully in detail, and actually interesting enough, we find out that in the wild type, this area is a loop, but in the modern global state, it's alpha helix. So that's why you can see alpha helix water is slower than the loop water. But of course, during the folding, complete folding, this alpha helix becomes the loop. So that's the only exception. So basically, for all this data, we can correlate the local chemical identity and also local geometry. So we get lots of the information, and we can get this. So that's the one example. I give you a little bit of feeling, this water. And later on, we did another giant system. It's a DPO4. It's a polymerase. It's an enzyme. So this protein has four big domains, and we design more than 10 mutants. Good news is this protein has a low tryptophan, so we are easily do mutation by one. We can do each domain. So you can see, for example, we can put the protein in the barrate. Use molecular biology, we can put the tryptophan in the barrate. And if we use the 10 angstrom interaction, dipole-dipole interaction, we can find out that all the water is very close to the protein surface, probably within 7 angstrom. So that's what we nearly call this water is first layer or second layer water. And if we tryptophan is a little bit exposed, you can see that some blue water come. Blue water is like a 9 angstrom or 10 angstrom or 7 angstrom close to protein surface. And this is a fully exposed optical probe. So here you have lots of the free type of water, and you detect also, you have the inner layer water detector around the protein surface. So very interesting enough for this optical probe, we can find out this emission peak from time 0, the emission peak stock shift, you can divide by 3 types. One is the very fast water motion in the femtosecond, which I show you very soon. And then you have the 2 time scale in the picosecond and the tens or 100 picosecond. Even you can separate this all energy. For the E1, for the mutant which has E1, this fast water, you can see if the tryptophan optical probe emission is less than 380 here, then for this kind of mutant, above 380, you have the energy E1 or tau1. You have E1, tau1. Then if you're below this, that means the tryptophan will move to inside. Then you don't have E1. That means you didn't detect the fast water. So that means this E1 with tau1, it is represent this outside water motion. So this is like a reverse ice ball. So actually, if you excite this molecule to non-equivalent, the first motion is outside the water. It's not close to water. Okay, it's a reverse ice ball. Okay, so you can see above 380, this is well known textbook. Everybody knows the tryptophan at the protein position, if above 338, it is protein close to the surface, So you can see, this is a buried inside, and all this emission will be inside here. So we really can correlate this dynamics we measured with all the protein property. Is charge, heavy charge, hydrophobic, all these things. So we get a bunch of the correlation. And then, most important, we can plot with temperature dependent. You can see beautiful linear. So basically, you can easily use a linear equation. You can get a barrier, get this dynamics, the barrier. Okay, gets barrier. And also, we measured this tryptophan rotation dynamics. We call the wobbling dynamics. And then you can see, for each position here, the water motion and this tryptophan motion, it is very linear correlate with temperature. Now, if we learn the physical chemistry, if two independent dynamics is well linear correlated, there's only one possible. Anyone has an idea? One possible. What the kind of possibility? It is barrier is the same. Has to be, right? You think about the Arrhenius equation. If you have the temperature dependencies all correlated, the barrier must be same, but the prefactor is different. So we have find out very interesting, this tryptophan also have two dynamics, very correlated with this water motion. So you can say for tau3 with tau3 solvation dynamics with wobbling dynamics also very correlate. Of course, the tau3W always larger than tau3S because this is an equal line here. So this is a really shock to us. It means this two motion is correlated very well, even the barrier is the same. Why I say this is important? In 1990s, the protein dynamics godfather, the Hans Flamfeld. I don't know if we're doing protein dynamics, you know, in last century, you know, the protein godfather of father. It is the Flamfeld proposed this slaving model. They say all the protein dynamics is slaved by water. Of course, the biologist is really against this model, is not happy. But published 4 papers in PNAS is well cited. If we look at this today, I check like 30,000 times or whatever cited. It's a well cited paper, and they say all the protein motion controlled by water. They use polymer language. They say, okay, protein side chain move by beta relaxation. This is polymer language. And the protein domain motion controlled by water is alpha relaxation. This is the corresponding polymer language, the theory. So from this data, it is true the side chain motion, it is slaved or controlled by hydration water. So at least this experiment, it is truly proved his idea, in my opinion, is right. So the water is slaved under the protein side chain surface motion by this dynamics direct measurement. And from this, we also can find out the barrier, and also shock to us, for each protein, you basically barrier more or less the same, by plus minus 0.5 kilojoule per mole, very small. This is Germany, actually, if you think about it deeply, this is very significant. I didn't show you, for temperature study, we studied like 5 or 6 big protein, bunch of the data. We find out that for each protein, the barrier is unique and all the same, even for each mutant at the different position of the protein. So in a sense, the whole protein water is like a dynamic audit. So each place you break the networking to do the dynamics fluctuation, the barrier is more or less the same, even though the prefactor is different for each position. So that means maybe the hydrogen shear layer, it is a very long ordered coherent type. And then, but it's dynamic the order, but each place you break the hydrogen bond networking is more or less the same. You can look at this here. The energy very small, even for this one. Let's look at this one. The energy is 10 kilojoule per mole. So it's only maybe less than 2 kilocal per mole is one hydrogen bond. So that means you let energy break this networking, just break one hydrogen bond for do water fluctuation there. So lots of the information here, we can understand the water, how it interacts with protein. And interesting, another information I show you here for this free water, this I think is so-called free type of water. And then prefactor, if we look at this prefactor, this is about 20 femtosecond. This is exactly we are talking about in the free water is the inertial motion. The water inertial motion is about 20 femtosecond here. And also the barrier is about 1 kilocal per mole. So this is type of water, okay? So there's lots of the information we can get to understand the water, how fluctuate with protein together. And also the dynamics is interesting enough. The time is in the picosecond. As you know, the free water here, if here is free water, the dynamics is 1 picosecond. This is 10th picosecond. And the protein fluctuation is, most of the people believe is 100th picosecond. So the dynamics is smoothly, is grading to the free water, okay? So it's a beautiful bridge on both sides, okay? So these all make a perfect sense. So finally, with our data, I just quickly summarize the things is here, we really can see the water-driven protein fluctuation in this potential energy surface, free energy potential surface, looks like a protein move fluctuation, water move, protein move, water move, protein move. So that's what we call this is a forbidden region, and then your fluctuation around this one, fluctuating to local minimum. And in the contour, it looks like lots of this rugged surface, and if you plot a hydration surface is the same. So basically, this all barrier is the same as I showed you before. So this water you can in relaxation to equilibrium state, and then your protein is in this rocket surface is a bump and back and forth. All these things. So we can get an idea. So now maybe I talk about the photoreceptor. We spend lots of the time to start a photoreceptor. We nearly cover from the UV to the infrared, and as today. People scientists discovered probably 13 or 14 different type of photoreceptor, okay? Use different chromophore. All this photoreceptor has an external chromophore. Only UVI is different. Use the intrinsic tryptophan amino acid as the chromophore antenna. So you can see this photoreceptor is highly regulated, especially for plants, flowering, growth, and then all the function, controlled by this photoreceptor. And then we even this cry, even people talk about it is molecular, is involved with circadian rhythm in a biological clock. People even claim cry even involved in the water birds, the migration. Still very controversial, this field, okay? And our vision, of course, is a photoreceptor. So here I give you one example, even we start all type, where I show you recently our work for past 6 years. We try to solve the puzzle of this UVR8. This is recently discovered in the field, this UV photoreceptor. You can think about for mammals, we can hide in the cave or in the building. We are not fear of the UV. If we think of the plants, it is very harmful. Scientists for a long time believe in the nature has the UV photoreceptor. If the system, species is exposed to the heavy UV light, the system will trigger some protection mechanism. So 10 years ago, scientists finally found out one protein, we call it, right now called UVR8. It is a UV photoreceptor in the nature. As many photoreceptor, this photoreceptor also is a dimer. Many photoreceptor is a dimer. Without a function is a dimer. With sense the photon, dimer become monomer, and the monomer to bonding bunch of the downstream protein to initiate a bunch of the biological function. That's the general function, working principle of the photoreceptor. And similarly, for this UVR8, this protein is a beautifully dimer, and then this structure, when they publish by two groups same month, one is by Yi Gongxu from Tsinghua, and then another by the Getoff in the script. And they are, one is in the Science, one is in the Nature, and the same month, and the same species, exact the same. Okay, they publish it side by side. One is Nature, one is Science. So when I saw this protein structure, I was very shocked. Of course, get excited. There are a bunch of the tryptophan. I mean, we believe we are probably one of the best group in the world to do tryptophan study. Since the water, we start out of photophysics, photochemistry is a very deep understanding tryptophan business. So we said, wow, this is God's gift to us. We can understand all these details. So you can look at this protein. Buried inside has a tryptophan ring. It looks like a photo antenna system, like a photosynthesis. they collect the light. At the interface, have C2 symmetry, and you have the 1 is a cluster, 3 plus 1, and 1 plus 3, and form the tryptophan cluster we call the reaction center. Among this center at the interface, you have the 3 tryptophan is a peripheral around this ring, this cluster, this one. So there are like 2 pairs here, and there are 2 rings here. This is highly buried in the hydrophobic environment, and this is the interface, also lots of the water around here. And at this interface, there are 32 hydrogen bonding and salt bridge. Let's think about it. Average, each hydrogen bonding and salt bridge, let's think about it, maybe 2 kilocalorie per mole or 3 kilocalorie per mole. So 32, this is around like 60 to 80 kilocalorie per mole, which is a carbon-carbon bond strength. And that means this is a rock. You no way you can easily to break it. Very high energy. So this protein is extremely stable. And then people find out in order to make a function, this dimer need to dissociate by UV light because they sense the UV light. And with the UV light, they dissociate and they can do biological function. So when we saw this, we say, let's do it. So just for simplicity, we assume this W is a WD because it is a distal away the surface. And we call this WC, this 4 is a center or a cluster. And the P is a peripheral among this center. So we separate this W into 3 groups, into 3 groups. In the lab, we did hundreds of mutants about this protein, 1 by 1, okay? We can separate this 3 group tryptophan 1 by 1. That means we only contain this tryptophan, all mutated this to phenylalanine. The dimer is perfect, structure is perfect. So that means we form the dimer, we get absorption. We can mutate also this W with only C here, 4 here, or we only have the P here. So we can get a 3 group absorption and the emission. You can see clearly this is center tryptophan. This is a peripheral. This is a barrier that we call the WD. This is 3 group 1. And you can see easily, you can immediately find out they can do forced energy transfer. Here, emission will overlap with the absorption. So we can see here, we do calculation. So this is a distal W to the peripheral. This is a coupling constant. You can vice versa, but it's very small. So that means the energy move is directional to the center. Same as to the interface. You can say this is distal to the pyramid. Pyramid, that means this is 4, WC, pyramid shape. So this is a much 1 order larger than this. Similar, peripheral also to pyramid. The peripheral W to the inside of the this 2, you can see it is also 1 direction. So that means this WC or pyramid W, it is energy sink. Energy sink. All the energy will flow to the interface, and at the interface, the energy all flow to the center. So all the UV light after this light harvesting will dump in the center. I call the reaction center. Looks like a reaction center in the photosynthetic system. So in the lab, we can figure out all this energy transfer. Just for simplicity, we don't tell you details. We can figure out that these hundreds, more than 100 pairs of WW energy transfer. And here I show you the data. So we know this each WD, let's say distal the lifetime. We can do 1 by 1 mutation, by 2 by 2 mutation, 3 by 3 mutation. We can figure out the 6WD. We treat the 6WD as like 1 system because it's really symmetry. We don't need to separate 1 by 1. So we can figure out the 6WD, go to the 2W or 3W, 1W. I just show you 1. We did all, okay? I just show you 1 example. And then we can figure out all the energy transfer details here by look at the time-resolved fluorescence spectrum. And here we also collaborate with the Johnny Gao to the long-range, long-time, the QMMM calculation. And then we found out the energy transfer the rate, of course, protein fluctuation, they are wide distributed. And this here, we show the QMM calculation, the energy transfer rate. This is we use the X-ray structure we calculate, because X-ray you have the direction well defined, we can calculate it. And this QMM is average all this, by the weight or the distribution. And here we show the experiment data with the theoretic data. This is experiment data, this is theoretic data, is really perfect match. So we feel very comfortable our measurement is right. In order to solve this, we set up 3 fluorescence techniques. One is upconversion, and then we do femtosecond time domain, and then we do a few picosecond or tenths picosecond. We use a single photon counting with the femto laser, and then we do the nanosecond even longer. We do traditional photon counting. So in order to solve this, we have to heavily use a fluorescence technique. One thing I have to mention, that when we do this in the world, actually many groups do this. Finally, all failed. Why? We figure out the trick. If we look at this absorption here, tiny here, you can see this 3 group W has different absorption. This one, red one, is only absorption extended to 320 to 325. So this is a WC absorption. WP absorption is here, extended here. And then this is a WD or WD global. So the trick here to solve this problem, which I show you more data to you, we need a selective pump WC, or we need a selective pump WP. So in this way, combine this selection pumping and the mutation, we can precise to understand this WC dynamics by exciting here, tiny absorption. Or we can exciting here, WP, we can solve the dynamics, okay? That's the trick we do this. Later on, we also solve similarly, we also solve the energy transfer, this one, 3, to this cluster. And we also find out all the energy actually finally dumped to the 2 critical tryptophan, W233 and the W285, okay, which I mention more later. So all the energy transfer to these 2 amino acids among these 4 clusters here. So let's quickly summarize. We really figure out the energy transfer because this is a 4 tryptophan among the total 13 or 14. Without the energy transfer, light harvesting is about 35% of quantum yield. But we find out that this is 40, this is 25. We found out that 40% you pump this, 13% transfer WP, 31% transfer WC. But the WP have 84% transfer here. If you add together total, so quantum yield enhanced by 73%. So basically, from 85 with this light harvesting and become the 73. But you might ask me, so it's a big deal? We don't know. Actually, maybe in the dim night, this guy, it is played a role here, at least from this, we should find out it is. Another main argument is why this energy transfer by evolution, all the energy will transfer 233 to 285. Why not this? Because as I show you later, this tool is extremely critical for the dimer dissociation. So that means this energy transfer by evolution absolutely is functional and important. Okay, I mentioned to you all the energy dumped to here. We found out that this one emission is quenched in the here. Okay, this emission. We did all the tryptophan mutation one by one. We found all quenched. So that means all the same. Only if you mutate the W33 or W285, the intensity increased to huge. Also, dimer never ever dissociate. That means this tool is extremely critical. Either I mutate this or I mutate this, dimer never ever dissociate, no matter how long you shine the UV light, okay? So that means it is true energy transfer here, you need to do some function. As the physical chemists, with this, started chemical dynamics for 30 years, we say, what happened? And the first thing immediately we know must be electron transfer. This tryptophan with electron transfer. Of course, we look at the literature, we couldn't find it. And then we propose tryptophan to electron transfer. And then we also measured the quantum yield. For this dimer dissociation by steady states, we're careful to calibrate. And we found out this dissociation. For Y type, it's 7%. For the total, this kind of dissociation is 7%, okay? And all other mutant, you don't need to worry about this. Oh, this one here, 10%. This is a tryptophan quantum yield. And this is a total dissociation quantum yield. With the water, with the D2O, same. That means the proton transfer lot involved. And then also for others. So 10% is a quantum yield for this dissociation, for this dimer dissociation. Keep in mind, but steady state measurement. And at that time, people proposed many, many models in the field, and it turns out all is wrong, all is wrong. So this is the key slides for this system. We say, if this guy do electron transfer, we have to measure the W plus, or W minus. W minus absorption we calculate in the UV, so it's not good for us. So we go to the major W plus. So you can see here, if we use the mutant as the control, because the mutant will not do separation, that means we're not do charge transfer. So because we muted these two critical, one or two both, we're not do charge transfer. So this absorption peak is a typical, this yellow one, it is the tryptophan excited state. And the people were alone by tryptophan with the chromophore in the solution. This is a well-known system, model system. Do electron transfer tryptophan with chromophore, you can measure W plus. And also many, many people study tryptophan plus spectrum is around 580, okay, peak absorption W plus. So you can see clearly we pump 290. At the beginning, we don't know. We just pump 290, pump every tryptophan. We do find out that in the 1 nanosecond, there's an absorption peak come out. And this peak shift to the 620, roughly. So that means in that environment, the W plus shift to red. And we tuned the 315, as I told you, we only excited the 4 molecules. That means you see very clearly this W plus come out. So it is true, we caught the W plus, it is electron transfer, okay? And later on, we also find out the deprotonation in this region for the W dot absorption, okay? But anyway, by dynamic measurement, we finally solved this dynamics. This is extremely important. W233 and W280 have charge separation. And then this charge separation, 233 plus and deprotonation with the D, okay, which we also studied. And this minus is extremely important with arginine to neutralization. Break first salt bridge, because this has a D here, they have the salt bridge with another unit. So this is a critical arginine. If you muted this arginine, and this protein will not formed, dimer never ever formed. So this arginine here is extremely critical. This is for many group study this. Arginine, if mutated, this dimer never can formed. So here, minus with plus and to charge neutralization. And interesting enough, WW energy electron transfer is 80 picosecond, as we measure here. 80 picosecond is quenching, 80 picosecond. Of course, only 75%. And then back electron transfer is 4 picosecond. So WW, it is not a favored reaction at all, it's up here. And then, however, we figure out charge and combination is 17 picosecond. So if you calculate, this charge separation is 75% quantum yield branching. And then this ET, electron neutralization, is 19%, because 80% is back to electron transfer to use this work. But it's good enough, okay? Good enough. So Haibing is here. When I visited NTU, I told Mabi, that time, 2014 or 15, with Mabi, and then I told Mabi this thing, we are doing this. Actually, she also published PNS, actually, unfortunately, and they put a plus here, minus here. creates the opposite. But of course, right now, we're thinking about it, it's impossible because the charge is here positive. So this is, we're not from positive, it's not stable. So actually, later on, we also use other method. We do W, Y, Y, W, all kind of thing. It is true, and this is a negative, this is a positive charge separation, okay? So we also collaborate with the Chinese, do the MD simulation. We found out with these two arginine, which I showed you before, it is true the water will come in. If you do charge combination with W minus the arginine, and then you will see water is coming in. And then also you see that subunit, these 2 units will separate. Will separate with. So this arginine become radical, and this is 2. And also water is coming in. And also this protein is rotated. And I have to mention one thing here. This protein is like a propel. And in the middle is a nanochannel have water. So when we do this charge separation in the WW, the hole is open. So even the channel water is move up, like as we showed here. The blue water is come out. But of course, the interface water also come in to solve the discharge, finally break this diamond. Let's summarize quickly. We figure out that the energy transfer light harvesting is 73%. And the discharge separation is 75%. And the charge recombination with arginine 90%. If we time this and this together, is 10%. So when we get this number, we saw that it's too good to be true because the study states, which I mentioned to you earlier, it is 10%. So we feel very confident the dynamics we observed by this time resolved study should be right, all the details. So this dissociation, and later on measured by the Japanese group, it is take a millisecond. Now, if this is right, until here, it is still in the picosecond time scale or 1 nanosecond time scale. So here already 10%. So that means this charge neutralization is the final step for dissociation. It's a downhill reaction. After this, from 1 nanosecond to 1 millisecond, the system couldn't coming back. Has to downhill to 100% to dissociation. Okay, so that's the way observed. Another thing is the water coming in, and then I told you this is 32 hydrogen bonding under the salt bridge. So we believe, or from our data, this first recombination is the flip of the first plate of domino effect. So that means as long as you do charge recombination, and then you just keep going. And what's the law of the water? I told my students early days, I say, even though your interface is very strong, if you want to destroy the strong building, what do? Flooding water. So that's here exact. The water all squeeze in. With this first step, the water squeeze in and finally destroyed this interface. It's 32 strong interactions. So that's we finished. By the time, probably we don't time, I skipped this probably the photolyze, which is our major work. I guess many people maybe saw our paper. So I just skip all the photolyze, the enzyme work. I back to the material I promised to say. So this DNA repair, I just skip all this DNA repair. Okay, actually. Okay, I do a little bit maybe recently published. Okay, the DNA repair has the dimer, and maybe I just give very quickly 5 minutes. I guess give details I'm not mentioning. So this is we spent probably 50% effort in the past 20 years, and we're still doing. So for biology, now I understand that for many groups, the group of people do one protein for lifetime. You will see many American people do one protein. Of course, it's not one protein, one superfamily protein do one eye. We did the same. This is a photolyzed superfamily. This protein has 2 categories, which are important. This protein very similar sequence, but have 2 major different functions. One is repair damaged DNA. Another is photoreceptor cry, which I mentioned to you. Blue photoreceptor, we study both, but you don't need to worry about this cry. I don't have time to mention. The photolyze we started in this family, they can study two damage. People were known by UV light in the nature. They formed this called CPD, cyclopyrimidine dimer, cyclobutane pyrimidine dimer, CPD, TT dimer, or 16-pyrimidine, which I show you structure later. So this family protein, if you look at this, according to species, have class 1, class 2, class 3, class 4 right now, also single strand, so the DNA repair. So this one, CPD, they repair this dimer, they can repair. Well, the basic idea is this is a flavin molecule with the UV light, with the blue light. This flavin has this is hydroquinone molecule structure is minus F80H minus. Absorb the photon, inject the electron to the DNA, and after receive the electron, this DNA repair down here. And the final repair, and the electron will return back, and then go photocycle one by one, the repair enzyme. For this protein, same family, but the whole is different. So this is couldn't cross this and this. So this fix 6-4, and then you shining light, electron to inject this 6-4 damaged DNA. Meanwhile, the histidine in the labeling inject the proton. After do all the rearrangement of the chemical bonds, and then repair the DNA, finally you proton back and the electron back. You can see it's very complicated chemical reaction in terms of PCAM. So we finally resolve all these details. I just show a photocycle. So for this CPD, we found out low species bacteria with high species, let's say plants, the dynamics structure same, but they use two different strategy. One is like a direct tunneling, another is the hopping, etc. So we figure out for each enzyme catalysis, each one involves 10 steps, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can solve the one by one, all the steps, and then we can figure out all the details, okay? And then we do all kind of the calculation, use Newton Marcos, this reorganization energy, free energy. We can figure out all these details for this protein, okay? For different species, yeah, just no time. And we also can figure out the electron tunneling this way or this way in the protein. We can figure out all these details about ultrafast studies, okay? So I just skip it. 6-4, we also continue. So 6-4, I told you, you need a proton transfer, electron transfer. And the early days, 15 years ago, we did this. And then recently, we did this. And recently, people found out by evolution, the 6-4 DNA repair, the photolyze, very similar with cryptochrome function. So recent years, just recent, maybe 5 or 8 years, people believe they found out that this photolyze or cryptochrome have the bifunction, dual function. Before I said either you do DNA repair or you do the photon receptor, and people believe this is a bifunction. So here we started this protein which called the cryptochrome photon receptor, but have 6-4 repair. So it is true, it is 6-4 repair. So you don't need to worry about this. Then we can figure out this. And here I want to mention is, recently we put more effort to focus on the population dynamics. You know, we want to remove the absorption coefficient. We put we know the dynamics. We can calculate the population dynamics. Why this is important? Because recently we do the XFE become big trouble. Because when we capture the X-ray structure, for example, at here, so it is a mixed species. It's not a single species. So for example, in the 2 years ago, we collaborated a bunch of people, did this photolyze, study dynamics by X-ray from the femtosecond to the second, all the details. And then we had a long, hard time to figure out that this structure belongs to who. Because I think, I told you, at this short time, you have a mixture of the species. So you need to know how to decompose all the species. So now we put the effort at this. So for this one, I was very lucky collaborate with Aziz Zenja. He really catalyzed, discover, partially discover and catalyze this photolyzed superfamily. For this, he received a Nobel Prize, 2015. Now back to material. I have 5 minutes talk about that. You know, we built this center in Shanghai ZHONG in the Ultrafast, and we try to do this all bunch of the lab to do electron, ultrafast electron, or optical, and then we haven't get a good theoretician to our group yet, but hopefully in the future we can get. But we do lots of collaboration. So here we build all the ultrafast, laser spectroscopy, 2D terahertz, all kinds of things. Okay. A very important thing is we get this electron. So we get the time resolved transmission electron, ultrafast. We already built ultrafast scanning scanning electron microscope, and also electron diffraction, all this electron business. So really for this one, which is most costly, use this time resolved electron microscope. Right now we can do diffraction, we can do morphology. This is not new and invented by Ahmed Zua in the Caltech more than 20 years ago, and the pattern is released 10 years ago. So actually, in the world right now, at least more 10 setup in the world right now, in the whole world. However, we have one very unique feature, which is the only one in the world right now. So what we do is we can do irreversible dynamics. That means you have the laser to shine in the light, for example, is melting, is a phase transition. We can use a chain of the electron beam. Right now we can become the line 16, 25, whatever, to continually to do imaging. So that means if we use the laser to melting this material, we can probe with a continuous like 4 or 9 or 16 or 25 electron pulse to record this irreversible process in real time. So this is the only one right now working in the world. Okay. So for example, here we can do electron diffraction. One laser shining, and we can delay the time. We can tune. We can put the 1 nanosecond, 100 nanosecond. We can take a snapshot to diffraction one by one. We can do lines. So this is extremely powerful for universal process to do dynamics, to measuring dynamics. Okay. So for example, this is our recent last year calibration. We built this machine. This is a static imaging of this scope. And then this is our use femto laser shining the system to do. Actually, we switch, take 10 minutes to switch. Static and the time, we just switch very quickly, okay? We can easily switch, yeah. Of course, we are laser femto pulse, so we expose 40 seconds. The image with a continuous one, thermal electron gun shining is exactly the same, the resolution. And then we also do this measurement. This technique originated invented by Livermore, Lawrence Livermore, the guys, and like 7-8 years ago. And then you can see here, they have the 75 nanosecond resolution. Right now, we routinely get a 30 nanosecond resolution. Well, you will say, well, this time resolution is horrible. You think when you do femto, you are nanosecond. But this is single chassis imaging. In order to get a single chassis imaging, you need enough electrons. So that's why you need to put more electron, the electron pulse will broaden. So that means that's the no choice, okay? We can push this laser to femto resolution, but we only have a few electrons. But then you couldn't do one chassis experiment. You need to do average. And do average, your process has to be reversible. Otherwise, you couldn't do that. So we have different option mode. This is called a movie mode. We can really take one shot imaging. We get data. And also we can do repeatable. Then we can get a resolution like a femtosecond or 200 femtosecond. So this is a 30 nanosecond single shot imaging. And it says so many electrons. So our special resolution is like a 6.5 nanometer. If we switch to the, we call the stroboscopic mode, which you can do average the reversible process, and then we can reach to like 5 astron resolution. Okay, depending on which experiment you are doing. So you don't need to worry this. I just skipped this. We did a demo of this. I want to show you one thing here. And this will show the nanoparticle jump time and the dynamics, the nanoparticle jump. But show one phase transition, maybe you're interested in this. So here we show that this amorphous silicon, and then to see the crystallization become the crystalline or the crystalline structure. So this is a typical low structure, a formless silicon. And we shine in the laser light, you can see there's no diffraction at all, more or less no. So this means that here silicon is liquid, is all become liquid. And then later on, you can see all crystallization again, the diffraction pattern. Of course, you will think about single to low isolation, not great. This is a very challenging experiment. And then this is more clearly. And we really can do this transformation, and you can find out this is standard here. This is standard, crystallization silicon, like this is 3 peak. This is very broader here. It is amorphous, okay? Also here is more broader. This is very sharp. So this silicon, you can see initial is this, and finally you can see even here maybe it's harder to see, but you have another ring here. This is a ring, this ring, this ring. So your really is time resolved is here. 3 peak, okay? Initial is very broad. So here is amorphous. So with all this, this is 9 snapshots. We just showed 8. Usually we take 9 snapshots. We can do analyze simulation, see after quickly melting, which very fast, this liquid, how long will it take to nuclearization? So this is a fraction of the nuclearization from the diffraction, okay, with the time by fitting this diffraction, the pattern. So we have lots of the data right now. We are writing something right now for this one. And for example, I show you an example, another for material people interesting. We here have this black phosphorus. And this is for 2D black phosphorus. And here, put in a hole, substrate hole, we just put these 2 material on here. And then we shine in the laser light, we can find out the initial every pixel here we analyze. It's random vibration, but at a certain time, they show the same vibration everywhere. So like a resonance shining. And then we do Fourier transform, and then we see what's the frequency. And then this way, you can see the material, property, all Young's module, number, all details. So do material it's pretty straightforward these days if you use this machine to do material. Yeah. So I probably finish here. Don't worry about this. It's good to have 2 master, to working together. So for many work is done in the Ohio. And then electron things is moved to Shanghai ZHONG. And then we have lots of the collaboration, and then also students doing the work. Yeah, I stop here. Thank you so much.
Thanks, Professor Zhong, for this wonderful talk. And also, we see a lot of advanced, like ultra-fast equipment. So I have a quick question. So can we send students to do experiments there?
Yeah, of course. Anytime. No, seriously. Anytime. We also need lots of collaboration together or do experiment. There's a bunch of equipment there. Yeah, that's absolutely. Yeah.
Okay. Questions from the audience?
Okay, thanks, Professor Zhong, for very beautiful work. So I can, I work on materials, and I can see, even with materials, ultrafast spectroscopy sometimes it's not easy because you get so many signals after you photo excite them because there are so many processes. And I can only imagine in biological systems it's going to be 10 times or 100 times harder because it's so complicated, right? There are so many things inside. So, for example, a quick question, for example, is when you photo excite them, right? I can imagine there are so many different signals in the absorption, transient absorption, for example, in the transient species, and many of them probably I would think overlap with each other. So how do you sort of decouple, different species, different signals, and also at a different time scale as well? Do you, for example, do global analysis or things like that? Is that a problem? Is it very difficult? I don't work in this. So.
Okay, thank you. Actually, for the photoreceptor photoenzyme, and the photoreceptor more or less, well, not to say easy, it's more specific because you have a chromophore. Yes. Your absorption is well long. So of course, with this chromophore, you maybe have different intermediate state. So I'm thinking about for complicated biology, it's more or less like an environment. Of course, you use this chromophore induce conformation. That's another topic. Here we talk about chemistry. Your chromophore do this. And I said charge separation, do this, analyze. After that, use chromophore chemical reaction. We call the primary dynamics. Induce conformation change. Then we use other technique to do again. So we just do, for photoreceptor, we just do first part of the photochemistry or photophysics. And then later on, actually we are doing right now for the dimer dissociation, we want to see if any detail from the nanosecond to the millisecond, how exact the dissociation, how this cell 32 interaction zip up, zip out, to this. So we will use another technique to do again. So we have to step by step. For photoenzyme, it's tricky. Photoenzyme usually right now, biological enzyme sounds simple, even use the QMM calculation. If you have 2 or 3 molecules to reaction, they usually involve maybe, let's say, 7 steps or 10 steps, right. And maybe have 6 intermediates.
Right.
And in this, it is true, you are right, it's not trivial. We do first need build a model. So you get a bunch of the data, right? You detect this, or even though we can use the infrared to detect some specific molecules. So you need to get a bunch of the information, and then you build, based on the calculation or based on common sense, you build a reaction model, whatever. Then you need a global fit, whole thing. Your model can fit every data you took. And then finally you get like our photolysis for DNA repair, which I don't have time to talk about. We measure all the intermediate state, one by one, and then you figure out this each step dynamics, and you put it all together and then match all the observation, and then you say, bingo, you
some
get
of the intermediates, for example, their chemical signatures are not known, right?
Yeah, that's right.
So
good news is most case is we do electronic spectrum. So basically,
right.
You these days you calculate, you get roughly where it is, okay. Right? So of course, we haven't, probably we do later on, we do IR detection for some special intermediates and radical. Yeah.
Right.
Yeah.
Okay.
Yeah.
Another quick question is, when you work on these enzymes or whatever biological systems, when you do their photophysics, right? You use very, ultra short pulse to excite them, which has actually quite large in energy, right? I was wondering if the enzymes they have any change, conformational change under the laser excitation, or is that an issue?
It's a very good question. Actually, I tell you, this is all experiment done by 10 to 30 nanojoule, 2 milliweek. You are absolutely right. Many people I will say is wrong. Our protein, if we use more than, typically where focus length is routinely 15 centimeter, whatever, like many people doing the same thing. If many protein we did a test. If we shining light 100 nanojoule, which is very light, very small, you shining the skin, you will not see anything. You didn't feel anything. By 1 hour, your protein conformation change. We can detect the signal, you see the change in the shape. So most experiment, the enzyme photoreceptor, the energy only 10 nanojoule, extremely weak. So for us to do experiment, we don't need much energy. If you go to read the paper, say this guy is 1 millijoule, we say, my God, he.
Right. But then the signal, I imagine, will be very weak.
Yeah, you true. It's not too bad. You know, transient absorption these days, you can easily get a 10 minus 5, 10 minus 6, even also very tolerable. Okay. The change, yeah. And of course, fluorescence, you can single photon. You know, right. you have the technical single photon. So it's handleable. Of course, if you want to do 2D, 3D, 5D, whatever. Now that will be challenging. You can, you know, most of the 2D you need a minimal sample. Yeah. That's another change. You know, right. If you want to get a big signal, you need to increase concentration. Yes. And then for biology, it's a challenge. It's very difficult for biology. Right. Yeah. That's right.
Okay. Maybe one last question. In one of early work, you mentioned the FRET, F-R-E-T mechanism. I was just wondering. How did you know it's a FRET mechanism? I saw you have spectral overlap, but did you do the study, say, for example, to exclude maybe it's not a Dexter mechanism?
That's a very good question. And Dexter usually shorter distance, right? More or less shorter distance. Right. So for the distal to the interface, the data is very long, 20, okay. Very long. So that's 100% is not flat, because also energy transfer is nanosecond, is nanosecond. And for the peripheral to the center, which you saw, it is a very short distance along the, right? Yeah, that's right. The short distance still flat, energy transfer, and then there you could have Dexter by energy transfer, and we did the theoretical calculation carefully, and we found out that still FRET is faster for that interface tryptophan energy transfer. Yeah, but in the center, of course, this guy need a dissociation. Energy will not help. Transfer has to chemical reaction. So that's why we say that this two tryptophan coupled. Oh, I forgot to mention, actually, before we find out, I forget one very good point that you raised. This 4 cluster formed exton. We can measure exton band. So actually, this electron transfer is exton-induced charge separation. So this 2 chromophore, 2 tryptophan, 233 and 285, even 2 formed exton, already formed exton. And the exton induced the charge transfer. Yeah.
Nice. Yeah. Interesting. Thank you.
Yeah.
Any further questions from audience?
Yeah. So I think I also have a questions about the DNA repair mechanisms, because I see some of your pumping laser, it's in the ultraviolet range. So it's like 200 or 300.
Yeah, that is a problem.
Yeah, so I can imagine this will also affect the DNA, right?
Yeah.
It will also cause DNA damage when you are trying to repairing it.
A very good question. Okay. Okay, you're right. Of course, you know, if it's shining longer, DNA it is damaged, right? Of course, in the system, we put all damaged DNA inside. You know, we need to synthesize damaged DNA, so we don't have good DNA anymore. So we make the protein, we make all damaged DNA, we mix together. Okay, you know what I mean? So we have the 8 TTTTT, and we shine in the UV light. You're right, we shine the UV light, we make damaged DNA. We need a shining long time UV light lamp for, 20 minutes, 30 minutes. Then we make all DNA damage. So they can form dimer, you know. So, and then we put this in the solution with the enzyme, they are bonding together. And this damaged DNA dimer, let's say dimer, or 6,4 pp, they bonding the protein. So after this, we shining blue light. The pumping is blue light. And flavin and do electron injection, a bunch of things. But you saw the UV light, even we detect the 238. We nearly go to the 900 down to the 240 or 230. That is a probe. The light is extremely weak. Because the transient absorption, you don't need a kill light, right? You do delta. So yeah, it is. So we nearly use this UV light to probe T formation, the T formation. T has absorption. We use the T formation. Yeah. So the UV light is extremely weak. So we are not to make any.
It's not further damage.
Yeah, further damage. Well, you are right. If this experiment is very challenging in the deep UV because the protein is not happy. We need to use extremely light, which many details I didn't tell. Many protein need cooling. We shining light probably by UV probe, even though very weak, we shine half our protein blood. So we need to cool down protein to 4 degrees, and then to do, and then can longer to maybe 1 hour, can finish experiment. So your protein is extremely unhappy when shine UV light. Protein, also protein, very unhappy shining UV light. Yeah.
Interesting. Good to know.
Okay, no more questions. Then we need to thank Professor Zhong again, and thank you all for the participation. Yeah.
Thank you.